Hi, welcome back. This is part 3 of 3H problem. In the last part, we got 5 solutions by using a different perspective. In this part, we are going to verify that these are indeed the only solutions by going through each conversation steps as we did in the sample scenarios in part 1. We are going to do that with the computer aid. So let us start. Now let the numbers of Albert, Brinda and Cain be A, B, C respectively. Let length of ABC be the number of conversations it takes for some student to claim his number finally. That is the conversation length. Note that in the original problem, at the 6th conversation, Cain finally declared his number to be 144. Every student before him has said that they don't know their number. So length of ABC is 6 and C is equal to 144. That is length of A, B and 144 is 6. So we need to find A and B such that length of A, B, 144 is equal to 6. At each conversation, the student may either say I don't know my number or may claim his number. Let us indicate the reply of the student at nth step as Sn of ABC. So at nth step, if the student says I don't know, then the statement Sn of ABC is equal to 0. At nth step, if the student claims his number, then the statement Sn of ABC is 1. So length of ABC is the least value of n for which Sn of ABC is equal to 1. That is the number of conversation it takes till someone can claim his number. For example, in the original problem, statement 1 means S1 of ABC is equal to 0. Statement 2, S2 of ABC is equal to 0. Statement 3, S3 of ABC is equal to 0. Statement 4, S4 of ABC is equal to 0. Similarly, statement 5 means S5 of ABC is equal to 0. And finally, statement 6 means S6 of ABC is equal to 1. So, the length of ABC is 6. Now, we are going to find a way to calculate the values of these statements. Before that, let us note certain things. As we have seen in the earlier part, each student reduces his number to 2 possibilities. Let us give names to these possible values for our convenience. Let us call Albert's 2 possibilities as A1 and A2, where A1 is absolute value of B minus C and A2 is B plus C. Let us call Brinda's 2 possibilities as B1 and B2, where B1 is absolute value of A minus C and B2 is A plus C. Similarly, let us call Cain's 2 possibilities as C1 and C2, where C1 is absolute value of A minus B and C2 is A plus B. Now, the other thing is, how can we know whose turn it is at the nth conversation? This is easy to find because each student's turn comes every third time. So, in general, if n mod 3 is equal to 1, it is Albert's turn. If n mod 3 is equal to 2, it is Brinda's turn. If it is n mod 3 equal to 0, then it is Cain's turn. So, these are the observations that we needed. Now, let us begin. So, we are going to calculate the values of the statements. Note, the value of the statements can be either 0 or 1, with 0 meaning I don't know my number. We are going to calculate statement 1, S1 of ABC, statement 2, S2 of ABC, statement 3, S3 of ABC and so on successively. When we get the value as 1 at some point, we stop there. Now consider statement 1, S1 of ABC. In the first conversation, it is Albert's turn. Albert has 2 possible values, A equal to A1 or A2. Remember, a1 is absolute value of b minus c and a2 is b plus c. So if a1 is equal to 0, then Albert can claim a2 as his number. That is, Albert says I don't know when a1 is not equal to 0. So s1 of abc is equal to 0 if a1 is not equal to 0 and is 1 otherwise. Now consider statement 2, s2 of abc. It is Brinda's turn. Brinda has two possible values, b equal to b1 or b2. Remember, b1 is absolute value of a minus c and b2 is a plus c. So if b1 is equal to 0, she can right away tell her number to be b2. If b1 is not equal to 0, then she checks both b1 and b2 to see what happens to the first statement. She knows that one of her possible values, which is the actual value, results in the first statement to be 0. That is Albert saying I don't know my number. So if the other value results in the first statement to be 1, then she can eliminate that number and claim the other value as a number. In other words, if for both of the values the first statement remains 0, then she says I don't know my number. So the statement 2, s2 of abc is equal to 0 if b1 is not equal to 0 and statement 1 remains 0 for both the values b1 and b2. We can combine these equations into 1. So it is 1 otherwise. Now consider statement 3, s3 of abc. It is Cain's turn. Cain has two possible values, c1 and c2. Remember, c1 is absolute value of a minus b and c2 is a plus b. So if c1 is equal to 0, he can right away tell his number to be c2. If c1 is not equal to 0, then he checks both c1 and c2 to see what happens to the first two statements. He knows that one of his possible values, which is the actual number, results in the first two statements to be 0. So if the other value results in any of these statements to be 1, then he can eliminate that number and claim the other value as his number. In other words, if for both of the values the first two statements remain 0, then he says I don't know my number. So statement 3, s3 of abc is equal to 0 if c1 is not equal to 0 and the first statement remains 0 for both the values of c1 and c2, as well as the second statement remains 0 for both the values c1 and c2. We can combine these equations into 1. So it is 1 otherwise. Now let us consider the nth statement with n greater than 3, as we have already dealt with the first 3 cases. Assume that we don't get the value 1 till n minus 1th statement. So we need to check the nth statement whether it is 1. Consider the case when n mod 3 is equal to 1. It is Albert's turn. He considers his two possible values a1 and a2. Note that we know a1 is not equal to 0. If it is, in the first step itself Albert would have claimed his number. So we don't need to check whether a1 is 0 again. So he checks both a1 and a2. He knows that one of these values, which is the actual number, results in all the previous statements to be 0. So if the other value results in any of those statements to be 1, then he can eliminate that number and claim the other value as his number. But he does not have to check all the previous statements. Just before two statements, he himself has said, I don't know. So he just need to check the previous two statements alone. If both of these statements remain 0 for both of the values a1 and a2, then Albert says, I don't know. So statement n, Sn of abc is equal to 0 if the previous two statements statement n minus 2 as well as statement n minus 1 remains 0 for both the values a1 and a2. We can combine this into a single equation and it is 1 otherwise. Similarly, if n mod 3 is equal to 2, it is Brinda's turn and we get this. And if n mod 3 is equal to 0, it is Kane's turn and we get this. So, finalizing our results for the first 3 statements, we have this, and for all the other statements, we have this. So, starting from S1 of ABC, we successively calculate the next statement's value, S2 of ABC, S3 of ABC, and so on till we get the value 1. If it is the nth statement where we get the value 1, then the conversation length is n. So we have found a way to calculate length of ABC. So to find the solution for our original problem, we need to find the values of a and b such that length of AB 144 is 6. If C is the sum of A and B, that is A plus B equal to 144, there are only 143 possibilities to check, like A can be 1, B can be 143, or A can be 2, B can be 142, or A can be 3, B can be 141, and so on up to A equal to 143 and B equal to 1. But if C is the difference of A and B, that is absolute value of A minus B equal to 144, then there are infinite possibilities. For example, A can be 145 and B can be 1, or A can be 10,145 and B can be 10,001, and so on. So we can't check all those possibilities. The good thing is this scenario cannot happen at all. The final claimed number will always be the sum of the other two numbers. Let us see why this is the case. Suppose the conversation length is 1. That means in the statement 1 itself, the student has claimed this number. That means statement 1, S1 of ABC is equal to 1. This can happen when Albert sees B equal to C. And so A1 which is absolute value of B minus C is 0. So Albert claims his number as A2 and A2 is B plus C, the sum of the other two numbers. Therefore, if the conversation length is 1, then the final claimed number will always be the sum of the other two. Suppose the conversation length is 2. That means in the first conversation the student says I don't know, and in the second the student claims his number. So S1 of ABC is equal to 0 and S2 of ABC is equal to 1. So consider the final conversation, that is again it is Brinda's turn. Brinda deduces a number to two possibilities, B1 and B2. If B1 is 0, then she claims B2 as a number. Since B2 is A plus C, the final claimed number will be the sum of the other two. Suppose if B1 is not equal to 0, then she checks both B1 and B2 to see whether one of them can be eliminated. Assume that the claimed number is B1. Then that means B2 has been eliminated. That is S1 of statement 1 is 1 when B is equal to B2. That is S1 of A B2C is equal to 1. But that means in the first conversation Albert has claimed his number and that is A. But note B2 is equal to A plus C, which means the final claimed value A is not the sum of the other two numbers. But we have just now seen that cannot happen, because when the conversation length is 1, the final claimed number will always be the sum of the other two. So we get a contradiction. Therefore, the Brinda's claimed number can't be B1. Therefore, D is B2, which is A plus C, that is the sum of the other two. Therefore, if the conversation length is 2, then the final claimed number will always be the sum of the other two. Now, having proved the first two cases, what if conversation length is 1 and what if conversation length is 2? Let us generalize it for any conversation length n by using induction. Assume that if the conversation length is less than n, then the final claimed value will always be the sum of the other two. Now consider the case when the conversation length is n. There are three possibilities. The final person who claimed this number can be Albert, Brinda or King. Let us see the first case, Albert, and all the other cases are similar. So Sn of ABC is equal to 1, which means one of the possible values of A1 or A2 got eliminated by Albert. Assume that the claimed number is A1. So A2 has been eliminated. That means either Sn minus 2 of A2BC is 1 or Sn minus 1 A2BC is 1. Note that the nth conversation is the Albert's turn. So n minus 1th conversation must be of Kane's turn, and n minus 2th conversation must be of Brinda's turn. Note that A2 is B plus C. So neither B nor C are the sum of the other two. That means either at n minus 2th conversation or at n minus 1th conversation, the claimed number is not the sum of the other two, and that contradicts our inductive assumption. That is, if the conversation length is less than n, then the claimed number will always be the sum of the other two. Therefore, this is a contradiction. So A cannot be A1. Therefore, A is A2, which is B plus C. Therefore, the final claimed number is the sum of the other two. We can prove the other two cases, that is when the last person is Brinda or the last person is Kane, in the similar way. Hence, by induction, the final claimed number will be the sum of the other two for any conversation length. So we have proved it. The final claimed number will be the sum of the other two numbers. Therefore, we have gotten some recursive statements which can be translated to the computer language as recursive functions. Also, we can check all the possible values to see whether those are the solution or not by using those recursive functions. Since the possible cases to check are finite, we can find all the possible solutions. Now, in this way, we can get the solutions for the general problem of any conversation length and any final claim. I give the C program link in the description below, and by this program we got the same 5 solutions again. So let us end this part with this. And the real amazing thing that gives surprising twist to whatever we have done so far is the story of the next part. Keep pondering. Thank you.